So if that timer up there, if I'm ever like talking and that timer's not going, then remind me, because that means I'm not recording. Okay, sometimes I forget. All right, so we're at the end of our first week. We have kind of done the intro. We started into chapter 13. We've talked about quite a bit about mass spectrometry. We talked about how the instrumentation works. Oh, do I have to? All right, just a second here. Let me pause. All right, so, okay, let's quiet down. We talked about how the instruments worked, right? We talked about the fact that we're detecting ions. We have to generate an ion. We can measure the mass of that ion, and that ion can also fragment into pieces, right? From the mass of the molecular ion is the ion that includes all of the atoms of the molecule. We can sometimes get information about the molecular formula, and we've gone through kind of a process in which we can do that. From the formula, we can calculate the number of unsaturations. Remember, unsaturations can be the result of either pi bonds or rings. And once we get that information, we can get additional information sometimes by the fragmentation. Okay, we talked about two types of fragmentations. One was called the sigma cleavage. Cleavage. I can't go too fast here, I guess. All right, and the other one, and this is just the cleavage of sigma bonds that we observe when we have alkanes. All right, and then there is the alpha cleavage. This is slow, and I want to go so fast. This is the cleavage next to a functional group. Okay, so I show you two examples of this. One is where we have, I don't know if this is going to work, carbonyls like this, and what we see is a cleavage like this with the ion going to with the carbonyl side. All right, so we'll lose an alkyl group. This R prime was a methyl, we'd lose 15 from the molecular ion to the fragment ion. If it was an ethyl group, we would lose 29. If it was a propyl group, we'd lose 43, on up like that. For alcohols, we can get a similar kind of, I'm not going to use that one. Dang, I just paid all that money. We can get the same type of cleavage. Oh, now I probably have to turn. Okay, the alcohols cleave in the same way. If we have the alcohol, it will cleave one of these positions adjacent to the alcohol with the cation going to the alcohol side. All right, so these are the two type of cleavage mechanisms we've seen. All right, so we're going to look at some more examples now. We're going to look at some more fragmentation and some mass spec examples, all right, comparing different structures like we started last time. After we finish that, we're going to start into infrared spectroscopy. And we're going to learn about how that works, what it looks at, and some characteristic absorptions that we can interpret in those spectra. Okay? Okay, so remember this stuff, those extra credit assignments are due on Monday, right? And then we'll start into the next ones. Yeah?
I have a question on those. When I go into look at them, it says that it's part of an unpublished module, so you can't look at it.
Okay, so you gotta, the question is, I think some of you are finding something that I don't even know is there anymore. So have you gone, so that all of these assignments should be in Connect.
Oh, okay.
So once you go into Connect, so I think you're finding somehow some old pretest or something that I used years ago, and it's
You just have to go out to connect.
go into connect. Yeah, and you should be able to click on the menu on the left under modules, and you can click on the assignments there, and it'll take you to connect. All right? Anybody else have any issues? Yeah.
There are some type of problem in the synthesis review. Like it says it has like 8 or 6 parts, but I always get stuck at part 3 or part 4 for some reason.
And it won't keep going further?
Yeah, and when I check the problem later, it shows like it's incomplete.
Yeah, okay. You have a comment on that?
So for those problems, that third part, it's just telling you like a summarization of what you've already done. You click next part, you just have to say yes, continue, and then you can see the next parts after that.
So there's nothing actually to do?
No.
You just click to continue? Okay. How many people I've run into, well, we have one student at least that transferred into this class and hasn't used the ChemDraw palette and all that kind of stuff. And I worked with her. Has anybody else in that situation? Do I need to put up some tutorials? Or you could, if there's just one, you could come and talk to me and we could look at that. There are some tutorials that I could post to, but I know that most everybody's already been through all of that. All right? Okay, so here's where we left off yesterday. We were looking at 2 mass spectra of alcohols. It says that the alcohols have a molecular formula of C5H12O, which gives us a mass of 88. So notice that in both of these cases, 88 is out here. And if I blew this up, there is a teeny tiny little ion right here, okay? But because that molecular ion is so small, it tells us that these alcohols fragment easily, okay? And so what we want to look at is from both of these, from 88, we want to look at the distance down to either the first ion that's formed, oftentimes, or to the biggest one. An important thing about all of these techniques, especially until we get to NMR, is that, for one thing, we're not going to be able to determine what each of these ions are. Okay, we're going to look at mostly the ones that are at the highest mass, because if we've lost a small mass, 15 or something, that tells us more than maybe seeing an ion down at 15, because so many molecules would have that, okay? And we'd like to see it, hopefully, to the base peak, if possible, all right? So we're not going to be able to identify all of the ions. Second thing is that mass spectrometry and infrared spectroscopy often just do not give us enough information to determine an entire structure. Okay, so the point is, each of these techniques are going to be complementary. So mass spec is going to give us some data. It may not be enough data to do the whole molecule. IR is going to give us some more data that will get us a little further along. And then when we get to NMR, that's going to be the one that gives us the most. Okay? All right, so this bottom one, we're going from 88 down to, this is 59. 88. And so, let's see, where's my cheat sheet for this one? Because I can't really subtract in my head. Is a loss of, what is that? Anyway, this goes down to, oh, that's the wrong one. That's the right one. Minus 29. All right? So what does a loss of 29 tell us? Right? We've probably lost an ethyl group. All right? So this is minus a CH2 CH3. And that's really the only big ion that we see that's in a higher mass. Okay? If we compare that to the upper spectrum, we go from 88 down to 73. So this is minus 15. And so that would most likely be a loss of a methyl group. Okay? Another important one would be then from 88 to the base peak, which is at 45. All right? And so this is a loss of 43. All right? And one of the main ways that we can generate 43 is by a loss of a propyl group. Okay? So what this is indicating then is the bottom one, we're really only losing ethyl groups. Okay? So out of a C5 molecule, we just draw out C5, where is the alcohol going to go? Right? We're going to cleave next to the position of the alcohol, and we're only have ethyl groups that are next to the alcohol. Yeah?
It'll be on the third carbon?
Right. It'll be on the third one or the one right in the middle, right? Because if we put the alcohol here, if we cleave on this side and the charge goes to this side, we get this ion of 59. If it cleaves on this side, we get the same ion. Okay? Because we're only seeing one main fragmentation. It suggests that maybe this is symmetrical and we put the OH right in the middle.
So the baseline is a propyl group on the top one?
The biggest one is the loss of a propyl group.
Okay. So why is it up? Why is 43 2 less than 45 up there? Like how? What is the explanation for that?
Well, this ion right here is at 45, and we get to that ion by losing 43.
Oh, okay.
Okay? It's kind of the difference between having a CH2 in there, which is 14 mass units, and an oxygen, which is 16, right? The two mass units different. So in this top one, we can lose either 15 or 43. So if we draw out this pentane group, where do we think the alcohol is going to go on this one? It's going to go with the second one in, right? If we put the alcohol here, then if it cleaves at this point, we lose a methyl group and we get this ion at 73. Oops, 73. If it cleaves here and goes this way, we lose the propyl group and we get the ion at 45. Okay? All right, so let's look at some carbonyl compounds. So these two aren't actually isomers, though. They have different formulas. So if we look at this formula here, how many sites of unsaturation does that molecule have? Just one, right? Because C5H10, the maximum would be H12, would be 2N plus 2, so there's one site of unsaturation. I'm already telling you that this is, if you could read that, it's a carbonyl, so that's going to be our one site of unsaturation. Okay? And so that really, if we have, again, 5 carbons, 1, 2, 3, 4, 5, and we're going to have a carbonyl, then there's actually 3 positions that we could possibly have it. Okay, we could put the carbonyl on the end. What functional group is this? It's an aldehyde. We could put it at the 2 position, or we could put it at the 3 position. Okay? This isn't really including if we had some branched alkanes, but we'll just keep it simple here. All right? So each of these would give us a cleavage next to the carbonyl. That way, we'd be losing a butyl group, right? And we'd only get something very small. Here, we could lose methyl or propyl. That's kind of like that alcohol that we had. The ions that we would observe would be slightly different, though, because there's an unsaturation in the ion. And this one would really only lose an ethyl group on each side. Okay, so what do we see? So the molecular ion on this one is at 86. So this is 86. This is the molecular ion. Okay, here's one at 71. Yeah?
On the last problem with alcohols, we counted the really small ion at 88. On this one, it shows one at 100. Do we...
Well, at 100, so I think, well, since I looked up these spectra, and 100 would be higher than the mass of the structure, so I don't know what that is, right? So if we were going from scratch, then that could be an issue, okay? But since we know what the molecular formula is, we'll just ignore that out there. Yeah. All right? So here's the possibilities. So we're seeing 86, we're seeing 71, we're also seeing 58 and 43, right? This is going to be minus 15. This one's going to be minus 43. Now, this one at 58 is kind of special, though we're going to ignore it. Note what's different about the one at 58 than the other fragment ions. It's an even number, right? Notice, remember that I said what's most common is if we start with an even number, we get fragment ions with odd numbers, okay? So what that even numbered ion means is that ion is being formed by cleaving 2 bonds rather than 1. Okay, and there's kind of a special rearrangement that gives rise to that, but the book doesn't have it in our case, and so we're not going to go into that. In fact, it's named after the guy that taught the spectroscopy course when I was a grad student at Cornell. McLafferty. It's generated called the McLafferty rearrangement. But so if we see an even mass from an even mass, we're not going to pay attention to that, okay, because we can get by without it. But so what we're seeing is loss of 15, so it means that there's going to be a methyl group that we can lose. We're losing 43, means there's a propyl group we can lose. Right, so which one of these possibilities seems to fit the data the most? Which one? The middle one, right? This one here, right? Because this has a methyl group on one side of the ketone, has a propyl group on the other side. Okay, notice that this one at 43, if we drew it out, would be an ion like this. Has an oxygen and 2 carbons. This also has a mass of 43. So a propyl group has a mass of 43, and that acylium ion also has a mass of 43. Yeah?
So anytime we see an odd number or an even number coming from an even number, we know to ignore it.
Well, you know that there must be some more complicated fragmentation mechanism taking place.
For our purposes, though.
Yeah, we're going to get by without it. Yeah. Yeah?
Is sample contamination ever a problem?
Of course. So the question is sample contamination important? So what I would say is if you were in the lab having your samples run, and experimentally that can always be a big problem. Hopefully the ones that we're drawing that are either in the textbook or that I draw from these mass spec data banks, they shouldn't have impurities in them. Okay? But because these are high energy, they can cleave and do more complicated things than we can easily rationalize. So sometimes there's ions that we can't say exactly what they are. Okay? But yeah, if you're in the lab, then contamination can be a problem. And one thing, from my experience, is you know, we would take a new compound, we'd isolated this new compound from a sponge or something like that. And we had been doing NMR, which is not a super sensitive technique, and we take it to the mass spectrometer to run the sample. Mass spec is very sensitive. And also the size of the peaks in the mass spectrum is more representative to how easily the compound ionizes than what its relative proportion is. So you could have a minor component, contaminant, that ionizes very easily and gives a very big peak. And so the person that runs the mass spec always took great pride in telling us how unpure our samples were. You know, it's really irritating. All right, so we better get going. I get too distracted here. All right, so the next one, notice this is C4H8O2. All right, so if we do this, there's only 4 carbons. There's also one side of unsaturation, so we have kind of a couple of easy possibilities, right? We could have a carboxylic acid. If we just move this inside, we could have, do we know what functional group this is? This is an ester, okay? Or we could move that ester one more position and we could have an ester like this, okay? So if we look at the mass spectrum, 88 is now the molecular ion, okay? We see a number of kind of smaller ions in here, but let's look at the big one, down to 43, just like we saw before. All right? So if this cleaves, if we cleave it in the same way as we saw above, it could cleave here, and this would lose 15, right? So 88 minus 15 would give us a very small 73. Okay, so that doesn't happen too much, a little bit. But the bigger one, minus 43, if we do this and cleave like this is going to be a loss of, what, 45, right? Minus 45, and that gives us 43. That gives us the same ion we saw up above. Okay? So, if we had the one above it, we should get minus 29. 88 minus 29, that'd be, well, like something else down there. Or this one would be minus 43. Okay, so out of these, this one is probably going to fit the best. Okay, so the ways we can do this, on the spectrum side, we want to start with the molecular ion and we want to look at what the losses are to some of the, either the higher mass ions or the base peak. All right? For the molecule, if we have a molecular formula, we want to think about what possible constitutional isomers we could have. And then we can think about, you know, what cleavages could be possible and what ions those would generate, and see which of those possibilities best fit the spectrum. Okay? Oh, maybe I did this wrong. Oh, I did, I added the wrong, that's why. This should be 45.
43 is what the base peak actually is.
And this is 43. Oh yeah, that 43 was the base peak. So 43, we're losing 45 to get to 43. So it's more that I can't subtract than the spectrum doesn't match.
I've got a quick question. So it seems as if whenever we've looked at our differences, we've always started from the molecular ion to some fragment.
Right.
Is it ever worth our time to look at fragment for fragment? And the reason I ask is because back at the mass spectra of alcohols, I found a pattern where we were consistently losing 18 mass units after having lost our first like ethyl and methyl group, which I wasn't sure if that was just coincidence or...
Right, okay. So the question is, most times what we've been doing is always starting at the molecular ion. and then measuring the distance to the mass distance to the fragment ions. Okay? That, in fact, is the most common mechanism. And it's less common. There are times that it can do this where you would do a sequential loss. Lose one group and then another. The more common places that I know of there is if you lose like a group next to a carbonyl, like we did, a methyl group, then it could maybe lose carbon monoxide after that. Okay? But I think usually we don't want to look so much for those sequential ones. Yeah. Yeah, question?
So in the last example, given that there was a distance of 43 between the highest mass and the base peak, why did we end up choosing a structure that had a loss of 45?
Okay, let's see if I can. All right, so mass spectrometry can also be, usually what we would do is be working with pure compounds, okay? But there are ways to analyze mixtures of compounds with mass spectrometry as well. And one way to do that is to couple the mass spectrometer with what's called a gas chromatograph, a GC, gas chromatograph, or it's for gas chromatography. All right? So chromatography in general are ways to separate molecules. All right. And did you ever do in lab, did you do thin layer chromatography? Okay, so that's just another type of chromatography. And so in every type of chromatography, what you have is you have a mobile phase. So in TLC, it's the solvent you use, and you have a stationary phase, which in TLC was just this silica gel that was on the plate. All right? And as the mobile phase passes over the stationary phase, the compounds are in equilibrium between dissolving in the mobile phase and moving or being adsorbed or stuck to the solid phase. Okay? And depending upon a compound's propensity to stick to the solid phase or dissolve in the solvent, different compounds will move at different rates. Okay? For gas chromatography, what we have is this coil up here. This is the column. And these columns can either be, the size of your finger, or they can be little capillary tubes. And usually the capillary tube is coated with a liquid on the inside. All right, so when we inject the sample into here, we heat up the sample. In order to do GC, the molecule has to be able to be vaporized. So it goes into the gas phase, passing through the column, and it either can just move in the gas, or it can dissolve in the liquid that coats the inside of the column. Okay? And again, it just either dissolves or vaporizes, goes back and forth between those two. And generally what we do in this case is separate columns based upon their boiling point. All right? So molecules that have a lower boiling point are usually going to spend more time in the gas phase, and they're going to pass through the column faster. All right? And so from that, we can get a graph like this, which just tells us intensity. And so this is generally proportional to the amount of compound versus time. So we're just observing these compounds as they come out of the column, and it gives these peaks. So you can have gas chromatography coupled up to various types of detectors. So you're just detecting the molecules as they come off the column. One interesting way to do that is to use a mass spectrometer as the detector. All right, so you can both just detect that they're there, or you can actually get a mass spectrum of each of those compounds that come off the column, and as they do it. So it's a very fast way to do this. And if you ever watch, NCIS or, one of these shows that has forensic stuff, they talk about GCMS sometimes. Yeah?
So each peak is a separate substance?
Yes.
In a mixture?
Correct. You start with a mixture and they get separated and they come off individually at the end. So ideally, they're all pure compounds coming off. You know, in practice, if you have a very complicated mixture, you could, in fact, have two that come off together. Right? That's just bad luck.
Just out of curiosity, like the modern versions of these machines, how big are they? Like?
Oh, they're like a oven size. Basically, because it has to have an oven, right? Because it heats up the column and everything. Yeah, so they're maybe this big. Yeah, question?
How do you analyze mixtures that contain compounds that would combust before they enter a gas phase?
Oh, well, hopefully you're not adding anything like a spark, or if it was something that was that combustible, then you probably wouldn't use this technique. And if they're that volatile, they may come through at a very low temperature, too. Yeah, so you'd probably have to use something different if it was so flammable you couldn't heat it up at all. Yeah. Yeah.
So the textbook reference this as a method for drug testing.
Oh, okay.
Is that still valid? Is that still?
Yeah, of course. So what they also have, so the question was about using something like this for drug testing. What in those situations, what they probably have is linked to this. In their computer, they have a big database of mass spectra. And so when the compounds come off, for one, they probably have the chromatograph part calibrated so that they know the time at which certain drug compounds or metabolites or something would come off the column. And then they can run the mass spectrum as it comes off, and then they could match the spectrum to the database. So they could do it, you know, for standard things that they're looking for, they could do it very quickly. Yeah, good point. All right, so it's time for infrared spectroscopy. We've talked about mass spectrometry. We talked about how it's done and how to interpret them, how to identify some of the formula, some of the fragmentation patterns and such. Okay, so now what we're going to do is we're going to go on and talk about infrared spectroscopy. So let's... Okay, so just a few things to remember, right? We know that the energy of the light is directly proportional to the frequency and inversely proportional to the wavelength of that light. Okay? For infrared light, remember this is essentially heat radiation. It's kind of an intermediate energy. And when a frequency of light matches the frequency of a motion within the molecule, either stretching of bonds or bending of bonds like this, then that light can be absorbed. But the frequency of the light has to match the frequency of the motion, okay, to be absorbed. Because different bonds are going to vibrate at different frequencies, different types of bonds will absorb different frequencies of light and therefore different functional groups. Okay? So we can have bonds stretching like this. We can have bonds bending like this, or they can bend together, or they can go this way, then go this way, right? Then go this way. They can do all kinds of complicated motions. And they have names for these, you know, scissoring and wagging and bending and all kinds of things. And each of those motions will happen at a different frequency, and they can absorb a different frequency of light. Okay? Like mass, we will see absorptions in the IR that we can't interpret. Right? So we're going to look for some very specific areas that we can try to interpret. All right, so if we have a simple bond stretching motion, we can kind of describe that using what's called a Hooke's law. So if you had physics, you probably learned about Hooke's law. So this is kind of a slightly simplified version here, but what we really want to do is just look at the relationships. Okay, so over here, this is going to be the frequency. Okay, both of the bond motion and of the light that would be absorbed. Okay, so we have K. K is just a constant. Okay, it's like 1 over 2 pi times speed of light or something like that. We don't really care. The important parts here is this F divided by M. Okay, F is the force constant, and for us, what this really correlates to is the bond strength. Okay, so for example, a double bond, carbon-carbon double bond, will have a bigger force constant than a carbon-carbon single bond. Triple bond would be higher as well. And so what we see from this equation is as we get a stronger bond, it will move at a higher frequency and will absorb a higher frequency of light. Okay? The other thing that's important here is M is the mass. Okay, so if we looked at the full equation, the mass is a little bit more complicated than that because there's actually 2 masses, right? One on each end of this spring. But we're just going to kind of generalize here. So because the mass is on the denominator of this fraction, the smaller the mass, the higher the frequency. Okay, so if we have small atoms, they're going to vibrate at a very high frequency. Right? If we have big atoms, it's going to be slower. Okay, so hydrogen, bonds to hydrogen will be at a higher frequency. If we have bonds just between carbons or carbons and nitrogens, those things, it'll tend to be at a little bit lower frequency. Okay? A couple of other important things to take into account. So in order to observe a stretch or a motion in the infrared spectrum, that stretch or motion must involve a change in the dipole of the molecule. Okay, because as it moves, if it has a changing dipole, it kind of creates this little oscillating field. Okay, so for example, if we have carbon monoxide here on the left, so let me say first, a dipole here depends kind of on 2 things. It depends on a difference in charge or polarity. It also depends upon the distance between those 2 charges. Okay? So if we take something like carbon monoxide, we have a plus and a minus, and as this bond stretches and contracts like this, the distance between those 2 charges are changing, and so we have a changing in dipole. Okay? So we would call this IR active. Okay? And it would be a visible stretch within the IR spectrum. Okay? Alternatively, if we look at carbon dioxide, it has 2 polar bonds here, and so as they stretch and come together, each one has a changing dipole, but because they're in opposite directions and equal amounts, they would cancel each other out, and there's no net dipole for the molecule. Okay? So the dipoles cancel here. And so this would be essentially IR inactive. Okay, and so even though that motion is taking place, we wouldn't absorb it. We wouldn't observe it in the IR spectrum. Okay. Now, carbon dioxide can have a different type of motion as well that would be observed. Okay, so this, what I've drawn here, is what we call a symmetrical stretch. Right, the 2 oxygens are going out like this at the same time. But it can also be that one of them stretches while the other one contracts, and it goes like this, and it's asymmetric. Okay, so if we had a stretch for carbon dioxide that stretched this way and contracted this way, right, then we would get a net, they wouldn't cancel out, and we would get a net change in the dipole, so this one over here would be IR active. So have you guys done IR in 2310? You never did that yet? Okay. One thing that's interesting when you will do IR, so there's a sample chamber and you'll have to put your sample in there. And what happens is that, usually you have to run a background spectrum, and then you put your sample in and you run your sample, and it'll take the spectrum of the background and subtract that from the spectrum of your analyte, right? So you're just getting rid of anything that was there the whole time that's not from your sample. But what can happen is you'll look into the sample and you'll go, and you'll breathe in carbon dioxide, and the carbon dioxide levels will be different between your background scan and your sample scan, and so you will usually see some peaks for carbon dioxide. The other thing that you have to watch out for is because one of the things that's very prominent in IR is OH, and we'll see that. It's very easy to see, but again, when we were talking about contaminations before, an easy contamination of an organic molecule is to have a little bit of water in there. It can be a little bit wet, and so water has OHs, and so you can get a kind of a false positive for an OH because you have a wet sample. So that's something to watch out for too. So other things down here, the position in the spectrum is in what are called wave numbers. So it's inverse centimeters. And so wave numbers are essentially 1 over the wavelength in centimeters, right? The wavelength would be in a distance, so we're going 1 over that, and this is proportional to the frequency. It's not an actual frequency measurement, but the higher the wave numbers, the higher the frequency, the higher the energy, okay? So just as a general trend. The second thing here, the signal intensity. So what we'll see, it's not only the position of an absorption that's important, but it's also the shape of the peak, how strong it is and how broad it is or how narrow it is. Okay, so if we have more polar bonds and there's a bigger change in dipole, the stronger the peak will be. Okay, also if we have functional groups like OHs or NHs that can do hydrogen bonding, that tends to broaden the peak. Okay, so these are just some general things. All right, so here's kind of a generic IR spectrum. Okay, so one thing that's different and weird about IR is that it's just flipped upside down. Okay, so the peak go down instead of up. Right, so you can immediately tell an IR spectrum. The reason for that is what we're looking at on the y-axis is called the relative transmittance. So this is showing us how much light is actually passing through the sample, which is essentially inversely proportional to how much is being absorbed by the sample. Okay, so up here at 1, because they're doing the relative transmittance, sometimes what you'll see is the percent transmittance, and you'll see a 100% up here instead of a 1. Okay, so wherever in the spectrum we see this going at the very top, that means all the light is passing through and nothing is being absorbed. Okay, so over that frequency or that wave number distance, nothing was absorbed. And then as we get peaks that go down like this, their relative transmittance gets less and less. That means very little is passing through because it's being absorbed by the molecule. Okay? Now we oftentimes split up the spectrum into 2 general regions. One is called the functional group region. Okay, and that goes from about 15 reciprocal centimeters. 1, 2, 3, 4, 5. So that's like in here. It'd be like about here. This direction. This is what's called the functional group region. And this is the easiest area to interpret, where most of the important functional groups will show up. Okay, the other part is called the fingerprint region. And that region, it doesn't look bad in this, but it can be very complicated. And so, like a fingerprint, it can be used to just match that part of the spectrum to some standard spectrum, right? Two compounds run in different spectrometers should give this a match on that fingerprint region. Even if we had two constitutional isomers, like we were looking at before, two different alcohols, you know, they're constitutional isomers, the functional group part would match up pretty good, but the fingerprint would be different, okay? This is just of a generic alkane. I always think about these alkanes as essentially having no functional group, all right? What it does have is this big absorption here, and this is a carbon-hydrogen stretch from an sp3 hybridized carbon to a hydrogen. And so that one is often very big. It's in many organic molecules have that. All right, so on Monday, we will look through a number of examples. We'll, to see what we'll expect. We'll work some examples, and then we're going to be hopefully jumping on into NMR spectroscopy as well. Remember, those extra credit assignments are due before class on Monday.